Welcome to this Air Quality Tech Talk. This series of Air Quality Tech Talk webinars covers key topics around technology and science and air quality. Please tune into the upcoming webinars to learn more about project experiences of air quality experts around WRI's program, like allies, partners, and global offices. The recorded webinars and slides will be available on the CityFix Learns Clean Air page shortly after this webinar, and this also includes past webinars. I can add the link in the chat box below. Today we'll be joined by Dr. Peter Clarko from the NASA Goddard Space Flight Center and Dr. Graciela Raga from the National Autonomous University of Mexico. Dr. Clarko is a research physical scientist in the Atmospheric Chemistry and Dynamics Laboratory at the NASA Goddard Space Flight Center. He leads research on the distribution and properties of atmospheric aerosols and their impacts on Earth's weather and climate system. His main research tools are global atmospheric circulation models and remote sensing observations. Dr. Clarko implemented and coupled the Aerosol module currently used for the NEO real-time forecast and climate simulation in the NASA GEOS 5 Earth System model. Dr. Clarko is additionally a co-chair of the International Cooperative for Aerosol Prediction, ICAP, a grassroots effort to coordinate the activities of global aerosol forecasting centers, model developers, and data providers. Following Dr. Clarko, we'll have Dr. Graciela Raga, and she obtained an undergraduate degree in meteorology at the University of Buenos Aires in Argentina, and a PhD in atmospheric sciences at the University of Washington in Seattle. After working in Toronto, Canada, and in Manchester, UK, she joined the Center for Atmospheric Sciences at UNAM in 1995. She's currently the senior scientist and head of mesoscale interactions research group. Composed of 3 young scientists and about 10 graduate and undergraduate level students, as a professor at UNAM, she has taught a number of courses over the year and supervised the work of 4 undergraduates, 10 master's level, and 7 PhD students, as well as 8 postdoctoral students. Her main research lines include topics in air pollution, aerosol microphysics, black carbon, cloud microphysics, dynamics, chemistry, and electrification. She has reviewed more than 90 peer-reviewed publications. And with that, I would like to hand it over to Dr. Clarko, who would be speaking about forecasting Saharan dust transport using the NASA forecasting model.
Okay.
Next slide.
Thank you. Can you hear me? Can you hear me?
Yes, we can.
Okay, great. Thank you very much for the opportunity to come and speak today virtually. I want to acknowledge this is a very much of a team effort, and I'm acknowledging some of my colleagues at Goddard who work on the modeling with me, as well as various data providers, some of whose data I'm going to show explicitly in this talk. And then especially my colleagues at the Navy Research Lab in Monterey are sort of my co-leads on the ICAP group, and I'm going to show you some of the results from the various models that are contributing to the ICAP ensemble. Next slide, please. So by way of motivation, I am professionally mostly working with global aerosol and chemistry transport models. I've had dust has been a big part of my career so far, from my PhD days to the present. You know, it's a fascinating subject to talk about because mineral dust particles are so abundant in Earth's atmosphere. And I think this satellite picture here makes that quite clear. I think this is from the Suomi MPP VIIRS instrument that's flying in space right now. And you kind of have to imagine the Earth tipped over on its side a little bit, with Western Africa at the bottom of the picture and South America at the top of that. But you know, these features of enormous Saharan dust plumes traversing the Atlantic, they happen every year, all the time. And you can see in the complexity of this picture too, the interactions of those aerosols with clouds. On the left side, you have the intertropical convergence zone, a huge area of convective activity. And even under the dust plume, you see the interaction of the dust with more popcorn kinds of cumulus sorts of clouds. This dust, an enormous amount of this dust comes across every year into the Caribbean basin. I've given a number here. It's about enough dust to fill the Empire State Building about 15 times. Can you mute on the phone if you're not speaking, please? Thank you. So on the next slide, please. So I come at this, again, from working with a global Earth system model, and I'm very interested in the interactions of dust and other aerosol species within the Earth system. And this little cartoon here illustrates, particularly for dust, some of the things that we're interested in studying here. On the right side of the picture, we have the emission region. I'm talking specifically about Saharan dust. So in Northern Africa, the winds blow across the surface and the dust gets lifted. It gets mixed at very high altitudes because of the deep planetary boundary layer that develops over the continent. And then the dust is advected to the west, going across the ocean, carried by the African easterly jet. And as it's transported, the dust level will generally gradually subside in altitude, getting closer to the surface as it goes across the Atlantic. Along the way, the dust is interacting with incoming solar radiation, reflecting it back into space, as well as thermal radiation from the Earth's surface. Dust is mildly absorbing in the visible, and so it can lead to a heating in the atmosphere where the dust plumes exist. That heating can cause a stabilization of the atmosphere, and that can act to somewhat suppress the development of convective systems, for example. But the interactions of dust with clouds are quite complex. Dust also is a nucleus on which ice crystals can form, as well as large dust particles can be giant CCN that will help activate clouds and therefore modify the properties of clouds and the hydrological cycle. Of course, we know too that dust eventually reaches the surface, and where it reaches the surface, we're interested in its effects on ocean biogeochemistry, as well as fertilization of land ecosystems. And then finally, and probably most relevant to this group too, is as the dust impinges on the surface, we're aware of and interested in its impacts on air quality and visibility and human health. The next slide, please. The model that I work with, the GEOS system, it's actually a fusion of a model with satellite observations through a process called data assimilation. And the figure on the left is from a long-term climatology of the model with the data fusion going on. This is a product called Merida 2. And what I'm showing here is the frequency of occurrence of high dust loading in 2 different months from this climatology. And so in March, we tend to see that the dust is transported a little bit further to the south and impacts more of South America. But in the summertime, in July, for example, the dust will travel further to the north, where it has the potential to really fill the Caribbean basin and reach Mexico and the US Gulf Coast states and so on. That seasonal pattern of transport there has a lot to do with the seasonal distribution of that intertropical convergence zone as it moves north and south with the seasons. And of course, that also plays out then in how the dust is impacting the surface locations. And the figures on the right kind of illustrate that somewhat clearly, where we have 2 sites, Cayenne in French Guiana on the coast of South America, and then Guadeloupe in the Caribbean islands. And the bottom panel shows a trace of a time series of surface concentrations at those 2 locations over a number of years. And what you can see is those distinct seasonal patterns, again, where at Cayenne, which is the red line down below, the peak in the dust concentrations at the surface tends to come a little bit earlier in the year, consistent with that picture on the left side. And then at Guadeloupe, the peak is a little bit later, more in the summertime. There's a line drawn across that figure also at 50 micrograms per cubic meter, which is a threshold. I think this is the WMO recommended 24-hour threshold for PM10 exposure. And you can see that frequently then the dust concentrations at these locations exceed that threshold concentration. Okay, the next slide, please. So I don't know how well this animation will play, but this is actually from our GEOS model. It's a high resolution, what we would call a replay. That is, we use historical meteorology to drive the simulation. And it's showing, in addition to dust, other aerosol species in the model. But the gray, the brownish colors that are pulsing off of North Africa is the main dust tracer set that's in the model there. And you can see in detail how the dust interacts with and gets wrapped up with tropical cyclones, for example. So GEOS is what our model is called, the Goddard Earth Observing System. It's a global Earth system model. It has a number of different applications, but the one that's probably most relevant to this group is as a forecasting system. And the group at Goddard that maintains and runs this system produces 4 meteorological forecasts, multi-day meteorological forecasts every day. And in the process, they're running the aerosol codes alongside that. So we're actually forecasting the distributions of aerosols like dust. I gave a web address down below that will point you to the location of the description of this model, as well as the availability of the data products from it. But it's a high resolution global system that is similar to other internationally recognized meteorological forecasting systems, but additionally has this aerosol package attached to it. The next slide, please. So just briefly, how do we go about putting dust into a model like this? And so the processes are coupled with the meteorology that's inside the model. In this cartoon up in the top left, it's an illustration of the physical processes that are going on at the surface that are emitting dust over a source area. And they're complex, and they depend on knowing a lot about the properties of the surface. The mechanism that we understand for the emission of dust is one that's called saltation and sandblasting. And that is when you've got a wind stress on the ground, larger particles that are on the ground will start to bounce along the surface. And those bouncing motion of those particles puts kinetic energy back into the surface, and it can fragment particles and releases smaller pieces that are the sandblasting. Now that's the part that gets lifted up into the air and becomes the dust that we see that gets transported over thousands of kilometers. But all of that process depends on knowing a lot about what the winds are doing, as well as the soil properties, the moisture at the surface, the presence of vegetation, and other things like rocks and plant and even buildings when you get into more urban sorts of situations. We have to kind of cope with that complexity, and we've simplified it somewhat as we put it into our models. We parameterize a lot of these processes in terms of this map now that's in the center of the figure, which is showing the global efficiency of locations around the world to act as dust sources. And we tend to scale the emissions then in terms of a function of what the surface wind speed in the model is, and this factor that's illustrated in the map, which is the efficiency of a location. And this efficiency factor that's shown here is a combination of the presence of bare erodible soils from a climatological map, as well as representing large-scale topographic depressions, which tend to be places where over historical times sediments have accumulated and are thus susceptible to being eroded into the atmosphere. So the next step in that process, after we have come up with an emission formulation, is we have to put it as a tracer into our model. That means that numerically we're tracking the concentration of the species. And dust is interesting because it covers a wide size range of particles. And because of that wide size range, we care about the differential processes that affect small particles differently from large particles. And so most models will try to discretize the distribution of dust into a number of what are called size bins. And each of those size bins has somewhat different representation of the physical processes acting on it. They're all transported by the winds in our models. But for example, the larger particles will tend to fall out more rapidly than the smaller particles through gravitational settling. And potentially they may have different interactions with clouds. And so the figure in the bottom left is showing from a number of different models that I've worked with over the years, how those size distributions are described, where each of the colors in those bars represents a different size bin. GEOS is at the top. We have about 5 size bins typically. And some of the models have fewer and some of them have more. The next slide, please. For the rest of the talk, I'll just focus on this June 2020 case study. It's very interesting. There was a ground-based campaign led out of the University of Puerto Rico this summer that was very interested in looking at surface sites around the Caribbean basin and measuring dust concentrations at the surface. And it was a little bit of a dismal prospect at the beginning of the season. In early June, there wasn't much dust in the basin at all. And these two figures are from my colleagues at Goddard from the AeroNet network, which is a ground-based sun photometer network that measures the column loading of dust and other aerosols as represented by the aerosol optical depth. And in early June, it's boring. Were very low amounts. But as you look toward the end of the month, on the next slide, please. I've circled now that at Barbados and Puerto Rico, the optical depths spiked really quite high later in the month. And this is this so-called Godzilla dust event, which is really quite exciting to look at. And I'm keenly interested in doing some further research to understand the mechanisms of this event. The next slide shows you a satellite picture of what's going on. The peak optical depth in the Caribbean was around June 22nd. And you can see from this picture here, which is from the NASA MODIS sensor on the Terra spacecraft, you can see very clearly the dust pulse that's really over Puerto Rico and the Caribbean islands right there. And on the next slide, you can see the progression of this over the next few days, where that dust is now migrated all the way over to the Yucatan Peninsula and up into the US Gulf Coast states and Texas. And this is truly an extraordinary event. On the next slide, I'm showing some air quality data taken from the US Environmental Protection Agency AirNow network of sites. And you can see all those red and orange colors along the US Gulf Coast states are places where the PM10, that is the concentrations of large particles at the surface, is really quite extraordinarily high. And they're such that this dust intrusion is pushing US Gulf cities out of compliance with EPA standards and above health recommendations from this external source here. So just the last couple of slides I've got sort of go through a little bit of the modeling of this event. So on the next one, of course, we're forecasting this happening. And as I said, early in June, there wasn't much action going on. But even about 10 days out before this event happened, you can see in the trace on the left there is the dust optical depth is predicted to start to rise toward June 22nd. The animation on the right is showing the model actually simulating the transport of this dust. As we get closer to that day, June 22nd, the next slide shows how the forecast changed and improved over time. Okay, so let's go to that next slide. And now what I'm showing is each of these different colored lines is a different forecast that gets one day closer to that June 22nd event. And you can see that first forecast was saying the optical depth would peak around 0.5. But as we got closer to it and the meteorology was better described by the model, you can see we actually got a little bit of a pre-pulse coming in around June 20th and 21st. And then the main event happened June 22nd and later, where the dust optical depth reached as high as 1.5, which is extraordinarily high for this region. So this is giving you a little bit of insight into how we look at this from a long way out, and as we get closer and closer to the event, we can refine our forecast until we eventually get something that kind of converges with what really happens. Okay, so the next slide, please. So I just have a couple of slides here about this group called ICAP that Ken mentioned at the beginning, and I'm a co-founder of this group. We started about 2010, and it was really born out of a recognition that it wasn't just NASA Goddard that was doing this, but that there were other meteorological centers around the world that were beginning to do global aerosol forecasting. And we ought to all get together and put our heads together and talk about how we do what we do, and develop best practices and communicate back to our centers about these activities. And so out of that, ICAP was born. And there are about 9 operational near real-time centers that are contributing right now their global aerosol forecasts to what we call the ICAP multi-model ensemble. And I've just illustrated at the top of the page here 6 different realizations from 6 different models that were simulating this June 22nd event that happened this year. And so this is it's a global consortium. There's the Barcelona Supercomputing Center, Copernicus ECMWF, the Finnish Meteorological Institute, Navy Research Lab, and Meteo France. There are other contributors as well, the Japan Meteorological Agency and the UK Met Office, et cetera, that are contributing to the ICAP ensemble. You can see in this figure that all of these models predicted the occurrence of this event, but they're very different in terms of the magnitude of the dust pulse and its extent, as shown by the colors, which are the optical depth again. So we're really interested in kind of digging into this and understanding why the different models came up with such different solutions to this problem. The next slide, please. And this is a summary then of the 10 years of this ICAP multi-model ensemble. This is, and I forgot to put the location here, but this is the dust optical depth at Cape San Juan in Puerto Rico over the 10 years of ICAP, where the black line at the top is the ICAP multi-model ensemble mean optical depth. And usually it peaks in the summertime at around 0.4, 0.5, but all the way over on the right side of this, you can see the line goes all the way above 1. So this is truly an extraordinary event. And to make it more clear, on the bottom, my colleague Pengzhan has stacked up all the ICAP models where each different line there is one of the dust seasons from May to August from the past 10 years. And the black one is this year, which is the one that really stands out as being extraordinarily high. This event that happened in June was over 4 times greater than the 90 percentile value of the dust optical depth. So it's really an extraordinary event in this case. My final slide is the next one here, is just a little bit of a summary here. So I'm interested in why this happened, what was unique about the conditions in this event right here. And so my hypothesis is there was anomalous and persistent weather system off the West Coast that trapped dust as it was accumulating due to its emission processes. And that's shown on the figure here. The black line is the dust emissions that are simulated in our model, which you can see that it's not so much that there's an extraordinary event of dust emissions happening. It's pretty constant through the month of June. But the red line shows that accumulation of the dust, where you get this high loading of dust over the continent that finally breaks down around June 18th. And so it was the movement of that weather system that then let a big pulse of dust squirt out. So I'll finish just with some questions about the event that I'm interested in looking into. What was the role of the dust radiative effects, radiative heating, in stabilizing the atmosphere, reducing cloudiness over the transported area, and thus prolonging the dust lifetime? What's the relationship between the meteorological system and the vertical distribution of dust, and how did that play into its lifetime? Why did the ICAP models differ so much? They have very similar meteorology to the model. So why did they differ so much in the predictions of this event? And then ultimately, what are the drivers of this kind of extraordinary event? And what can we say about the likelihood for these events in the future? And I'll stop there. Thank you very much. And I think we'll do questions later.
Yes, we'll do questions at the end. If anyone has any questions, I would love for you to leave it in the chat box below. Thank you, Peter. Very interesting conversation you've started. Can't wait till the Q&A session. And with that, I will stop sharing and let Dr. Raga share her screen and presentation.
Okay, hello. Can you see my screen, Ken?
Yes, we can.
Excellent. Thank you for the opportunity to talk to this group. And the way this webinar has been scheduled provided an overview and the modeling capabilities that just Dr. Clark mentioned. And now we're going to go into more of a process studies and in situ observations that happened in the Yucatan Peninsula as part of the Adaboy project, which is African dust and biomass burning over the Yucatan. It's a collaborative process with quite a few participants, as you can see listed in this slide, that happened over 2 years, 2017 and 2018, as you will see in a few minutes, to really characterize the arrival of the African dust onto the Western Caribbean and the Yucatan Peninsula. Because if you saw in the earlier slides, it's the probability of arrival, or the frequency that was shown, is not very high. So it's not often, but there are some events that do arrive. So without more, I'm not going to talk about the hazards to health of pollution. I want to discuss a little bit the role of particles in cloud formation and precipitation development. Was mentioned also earlier as cloud condensation nuclei and ice nucleating particles especially, and that's what we're going to focus here. And in terms of the Yucatan Peninsula as an area of research, of study, it had not been characterized very well in terms of its main pollution sources, and we really don't have a baseline pollutant concentrations yet. So, so it's an opportunity to go and study the region before it develops further. Furthermore, the impacts on precipitation development and the hydrological cycle have not been assessed there yet. The sources in the region, I'm going to talk about 3 types. The urban sources, the well-known ones that are anthropogenic and usually typically local in extent. Then the Yucatan is subjected to agricultural sources that also are anthropogenic and are local, but can be regional in extent. This is related to, mostly to burning of crop residues and preparing the soil for the following year of crops, but it's also related, and the emissions are much higher when the burning occurs of brushland and more woody vegetation, that it's used to clear the land and expand the agricultural frontier. So then there are, of course, natural sources that provide aerosols in the region, and gases, of course, and those are related to the marine aerosol, the marine source, which is the marine area surrounds the peninsula, and the remote production and arrival of African dust. So in this talk, I'm going to concentrate mostly and show some results of marine and African dust, but recall that we have done characterization of the baseline of urban sources as well as the agricultural sources and during the biomass season, which is separate from the African dust season. At the end of 2015, UNAM installed complete monitoring station for all criteria pollutants in the city of Merida as part of the interest of UNAM to become a truly national university and have representation in all states of Mexico. So the first evidence of the arrival to the surface in the city of Merida was shown in this picture in July of 2016, where you can see several peaks that I have circled, compared with very low average concentrations of PM10 and PM2.5, which indicate that Merida is a fairly clean city of about 800,000 inhabitants. Furthermore, as Dr. Clarko was saying, you take advantage of the reanalysis MERA-2 produced by NASA, which is, relies heavily on the data assimilation of satellite products, to show that in the 20 years from 2000 to 2019, this is the arrival of African dust to the Western Caribbean. And you can see in these 4 panels, the monthly means for June, July, August, September of the PM10 at the surface associated with dust. And clearly we see that the month of July climatologically is the one that is most active in the Western Caribbean, even having higher frequency or higher loadings than climatologically in Puerto Rico and Miami. So as part of this, this motivation, we put forward this Attaboy project to identify a series of objectives and that have to do with the background aerosol in the peninsula, characterization of biomass burning episodes and its role in air quality, and the African dust events that arrive in the peninsula. So Yucatan it's a very interesting, unique location at the crossroads because biomass burning from Mexico, but mostly from Central America, affect the peninsula, and also aerosol dust from remotely affected sources can also affect the peninsula, which is typically most days is clean, but when it's dirty can be very dirty. So 2 of the main objectives of our project was to characterize the microorganisms associated with the particles in these 2 types of air masses, and more importantly, to understand the sources of ice nucleating particles related with these non-local, remotely advected particles, and their abilities to generate crystals inside clouds, and that therefore catalyze the precipitation development in those clouds. So we have, as I mentioned, the continuous measurements of all criteria pollutants and in the city of Merida. And we carried out 6 intense observing periods, 4 in Merida and 2 in the coastal village of Sisal, as I will show now, in July 2017 until mid 2018. So here in the central photo is the location of the Yucatan in the Western Caribbean. And in the top panel, we show an image of the coastal village of Sisal with less than 2,000 inhabitants, mostly tourism and fishery, and where UNAM also has a campus. And the city of Merida, as I said, more developed, but it's a medium size right now, fairly clean, and we use the facilities of the College of Chemistry of the Autonomous University of the Yucatan. I don't want to spend any time, but on the specifics of the instrumentation, but you can see that here the rooftop of the College of Chemistry with the additional instrumentation that we took for our intense observing periods. In Sisal, you can see that the sea is very, very close, around 20 meters from the building. And again, we use the rooftop to make measurements. And on the lower left, some of you may not have seen, those are biostage impactors to collect particles in different culturable media to determine bacteria, well, microorganisms, as we will see later. We had both in Merida and Sisal. So, so as I showed in 2016, for 2017 and 2018, we did have some pulses of African dust. We they are in these two panels, we showed PM10 and PM2.5, again, PM10 in the blue, PM2.5 in the orange, and several peaks that have been surrounded by squares here, rectangles, sorry, and those have been identified or traced by back trajectories to remotely affected African dust. As you can see, some events have very high PM10 concentrations and PM2.5 as well, up to instances that more than 300% about the background. We also showed some of the World Health Organization standards. But is it really African dust? Not only because of the back trajectories, we looked at the vertical profiles from the soundings released in Merida for days that are shown in July 2017 here on a day that it was clean, the background in blue, and it's shown here, shown down below in the soundings, and a day influenced by the arrival of African dust. And so you can see that this is the mixing ratio, water vapor mixing ratio as a function of height. And we see that the boundary layer is very moist, typically the same on a clean day and a polluted day. But look at the very, very large decrease in mixing ratio or relative humidity in the region between 2 and 4 kilometers, associated with also stability, which are characteristics being reported by other studies of the arrival or the presence of what is called the Saharan aerosol layer over the Atlantic. Furthermore, the MERA2 reanalysis shown here, PM10 from dust as a function of height and day of the month. So for 2017, we saw that very large concentration that I was just talking about of PM10 at the surface, but now we see it throughout the vertical with peaks also at higher up and reaching 4 kilometers. But look what happens in 2018. We had many more events of African dust plumes reaching the Yucatan. So it's a very large variability which needs to be understood, and it is probably related, as Dr. Clark was saying, to the what is happening over Africa. So in order to further confirm the presence, we did chemical speciation, and here we look at 2 cases, one background and one during that plume in 2017, of the elemental composition by X-ray fluorescence, and we see very large increases. This is silicate, for example, shown here in the background, and becoming much larger, as well as iron, aluminum, and some other elements that have been shown to be related to the composition of our African dust. We also had the aerosol size distributions in Merida, both in Merida and Sisal, to be honest. And here I show in the blue a background number size distribution. This is related to what Dr. Kelargue was saying in terms of the size distributions that are included in the models due to the associated with the emissions. So we see in the submicron, here we go from 0.05 to 10 microns in equivalent optical diameter. And this is the logarithm, I'm sorry, the number concentration normalized by the size bins. And we see that when the African dust plume arrives in the yellow, we see increased concentrations in all size ranges, not only in the ones that were expected, larger sizes, but also in the submicron particles. And we convert this to a volume size distribution, and it clearly shows that, that there is a lot of mass, well, if we multiply by the density, and in the 1 to 5 micron range, but there is also a lot of mass in the submicron range. So keep in mind that these large concentrations of very small particles have very long residence times, and these have been seen in near Cape Verde near the sources. So these particles are enhancement here is almost a factor of almost a 2, I think 1.8. Those are not urban particles. These are associated with urban dust. So how about the microbiota? In order to do that, as I showed, the biosampler, different media are used, and then the microorganisms grow, are counted, separated, and sequenced. This is a summary for bacteria identify and fungi propagules, both in Merida and in Sisal. I have a lot of information here. So if we consider first Sisal, in 2017, we have examples of marine air. So both bacteria and fungi associated with the background marine. And we see that when the African dust arrives into the region, very large additional bacteria and fungi are seen in terms of concentration of the colonies, forming units. That's, so from marine background. But also I want to show the difference in Merida, where we sampled in 2017 and 2018. So recall that 2017, we only had one event, really massive event. Instead, in 2018, we had several. And we were able to confirm that there is an increase in concentration of microbiota associated with this African dust plume arrival. But we know that there is a large variability between them. So that's important because it contributes to the local pollution. So now we're going to take a bit of a breather and talk about how precipitation is developed in clouds, especially clouds that have large vertical extent, which are mixed phase clouds, because they have liquid droplets and ice crystals. So there are, as I say here, several mechanisms for the production of ice crystal formation, but we are going to be talking about this particular mechanism, which is called immersion freezing, and we will see shortly why, in which aerosol particles are called cloud condensation nuclei, are activated and have become cloud droplets that have intrusions that are insoluble and can be active as cloud as ice nucleating particles once the particles ascend and the temperature decreases and reaches, the sub-freezing. There is one interesting point in that the most efficient particles that catalyze the formation of crystals will become crystals at temperatures warmer than a certain threshold, closer to the 0 degree. Because if we have crystals that develop already midway in the cloud, then the microphysical processes that lead to precipitation development can develop much faster than if crystals are advected all the way to close to minus 30 degrees. So we want crystals to be developing in the lower or middle part of the cloud in the tropics, and that will develop precipitation much faster. So in our lab, under the leadership of my colleague, Dr. Luis Ladino, he has developed a cloud chamber and this is equipment called Moody DFT, which simulates the immersion freezing processes that I was talking about. And that is one of the few similar equipments that are available in the world and has been validated in a blind round robin type project in France, and is doing very well. So we have confidence that the results are valid. So this figure is a little difficult to understand because it has now the concentration of the ice nucleating particles as a function of the temperature when the first crystals develop. And that is called the freezing onset temperature. And the different colors represent in this diagram, represent marine aerosol, African dust in the yellow, and then biomass burning in the red. As you can see, the most efficient aerosol are the background marine that can can develop crystals at a temperature warm enough to -5, so very close to 0. But we see that African dust can do that at -10. So fairly warm freezing onset. And the pie charts in the bottom show something very interesting, that the majority of the contribution to the ice nucleating particles is in the super microns, or above sizes above 1 micron, but between, this is for the marine aerosol, about 80-20, but for the African dust is about 70 and 30 as well. So there is a large fraction that, a significant fraction, about 30%, that can be active as crystals in the submicron category as well. So to conclude, I have selected a few conclusions because, as you know, we have many conclusions, but we have confirmed in situ arrival of African dust by different methods and technique. They do affect air quality in the Yucatan, especially in the urban setting where it can mix with the urban aerosols. We have confirmed that the bacteria and fungal propagules are higher upon arrival of African dust plumes. Also that those particles are very efficient ice nucleating particles at temperatures warmer than -20. And they were found to be more efficient than the others, of which I have not shown. And I want to point out that this is an invaluable data set that we have gathered these 2 years that provide a baseline for pollution and as the Yucatan develops and grows in the future. But the takeaway is that the African dust particles have the potential to influence ice cloud formation and affect precipitation development in the Yucatan. I just want to show the acknowledge all the students that participate and also some colleagues and technicians. These are all the publications. Some of them are already published and available. Others are in review still. And this is what happened in 2019 when we did not have our project going, but it is continuing. Thank you.
Thank you, Dr. Raga. So now we're going to move into a quick Q&A session. WRI's Beatriz Cardenas from WRI Mexico will be facilitating this. If you have any questions, I would encourage you to add them to the chat box below so that we can go through them. And with that, Beatriz, I'll hand it over to you.
Dr. Colarco, Dr. Raga. It was great presentation. Really, thank you so much. As you may notice, and just as we told you, this series of TED Talks, we have some colleagues from different offices of WRI that are both from their quality and from other groups, but we also have as participants of these TED Talks a lot of colleagues from different cities that are working on air quality. So we think that I mean we saw in the media that it was very, very well covered, the African dust transport, and we saw a lot of news in the newspapers, in the radio, and we also think that this is a good opportunity to recap and think about how air pollutants move. How can we know what is the impact in our air quality from different sources? And I guess you both explained very well how this extraordinary event, as Dr. Colarco says, but also has happened over the years, as Dr. Raga has mentioned, in the Yucatan Peninsula, can tell us a lot of how to understand the sources and the transportation. My question here is a very general one, and I will go later into detail. What do you think that could be, I mean, as a lessons learned from this extraordinary event that we can capture to get better ways of transmit to the citizens and to different public policy officers the importance of two things: where the sources are, what are the sources of our air pollution, and the importance of studying these phenomena. Would you like to comment about it, Dr. Colarco, Dr. Raga?
Well, I can take one angle on that a little bit. It's, you know, in the lead up to this particular event, it was forecast days ahead of time and picked up by the media days ahead of time before the dust had even reached the Caribbean or impacted the U.S. or Mexico, and it was exciting to see models like ours being picked up by the media to communicate what was predicted to happen. And you know, I think we're moving into a time when we have tools like this that are you know, complement weather forecasts that people are used to. And so now we're adding another dimension to that, which is the chemistry or the aerosol or so forth. And I think it's also useful to remind people that there are a lot of people that are doing this now. And ICAP, which I talked about, primarily focuses on global meteorological centers, but there are a lot of groups that are doing these kinds of forecasts with a more regional focus. And often those people with a more regional focus have more experience with that particular area. So, you know, at the same time as we were looking at this event with GEOS, there was a group from Barbados that was running a regional system called WRF-Chem that was predicting these kinds of events. And especially with dust, the World Meteorological Organization has, for a number of years, had what they call, I think it's called the Sand and Dust Storm Warning and Advisory System, SDS-WAS. And there are, I think there are currently 3 different nodes around the Earth that are sort of collating both global and regional model forecasts of dust activity, and trying to disseminate that information to stakeholders in those regions. So I think, you know, using an opportunity like this to get some visibility for the fact that these kinds of systems exist and have some utility is encouraging, and kind of helps to keep us motivated and going with our activities as well.
Yeah, if I can add some things from the point of view of cities, I think it is very important to know the urban mix that is polluting the city more or less. As I was saying, Merida actually is a fairly clean city in terms of the urban sources, typically transport and electricity generation, waste management. Those are typical sources in every city. So so once you characterize that, which could be reaching hazardous levels to the population, you have to consider these events of advected pollution that provide a different mix of particles, different size distribution and different composition. So as we showed, a lot of the dust particles are small, and those will have very long residence times in the atmosphere. And those are the ones that will penetrate further into the respiratory system and get to the alveoli. And those can have elements that can affect negatively the body, especially some minerals. So that is very important to use these tools, forecast tools, to know and prepare the population for the arrival, because we also showed in this presentation, I only showed the increased concentration of microorganisms, but I did not go into the details that the papers already published of the different genera and species of microorganisms. They are not the same. It's not the same mix in Merida when we only have urban aerosol and biogenic sources of these from the ocean and from the vegetation. When the African dust plumes arrive, we have different microorganisms that we have confirmed. So, so that is important to warn the population, because they may be more vulnerable to these foreign pathogens than the regular mix. So officials, city officials or environmental or air quality officials have to be aware that that the mix of pollutants will change, and they have to characterize them to be able to warn their populations.
Thank you both so much. I guess that wraps up a lot of the potential questions. I would just like to mention that there is a comment in the chat from Babay. Babay is from WRI India, Air Quality Team. And he mentions that Delhi receives dust storms not only from local sources from Western India, the desert, but also from across international borders, in this case is the Middle East, during summer season, especially in April and May, which is spikes up the air quality in the region. And this goes along with what Dr. Arraga was mentioning. Yeah, I mean, air quality officials, air quality researchers, they need to know where what is affecting the local air quality, and important not, I mean, to transmit that to their citizens and to the officials who have some, at least some potential to to send some awareness to the people. But it's very important to characterize, and I will take back what Dr. Arraga was saying. It's important to support and continue this type of research. And as Dr. Colarco was mentioning, to do some joint efforts among the scientists to try to answer these questions that arise. So we look forward to the research that you both are doing, and probably in a few months we can have like an update what you have found after this extraordinary event, and continue the rest of your research. We thank you so much. We are almost on time. I will just like to tell the audience that this webinar will be posted later on in our WRI webpage, Tech Talks. So, and we will keep you posted for the next Tech Talk. So thank you so much, Dr. Colarco, Dr. Arraga. Thank you so much for your time and for sharing your experiences, your knowledge. Thank you so much.
No, not at all. Thank you.
Thank you. Thank you very much.